Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. We were discussing the thermodynamics module, and this is your lecture 18, and in the previous lecture we were discussing that how from the understanding of the bedrock geology we can design the basic reactions and equations that will help us that will provide a framework to understand the dissolution, precipitation reactions, weathering reactions that forms the basis of the natural water composition of lakes, of rivers, of any terrestrial aquatic systems. So, in the previous lecture we were discussing about these basic thermodynamics laws, some of the variables that is very useful, the types of energies we have, that is heat and work, and from here on we are going to work with this Gibbs free energy, because our aim is to try to find out three things. First, we need to understand equilibrium. What is the chemical equilibrium? We need to understand how to find out whether a reaction is going to happen or not. So, for a reaction to happen or not, whether it is a spontaneous reaction, whether it is a non-spontaneous reaction, we need to find out the Gibbs free energy. So, for that we need to find the del G R, that is the Gibbs free energy of the reaction, and to calculate that we need the delta G R 0, which is at the standard temperature and pressure, and also we need to find out the delta G F 0, that is the formation, the energy need for the formation of particular phases, of particular phases. That means it can be a particular mineral is there in a particular phase. So, for that mineral, for that phase, say suppose CaO, calcium oxide is there. So, what is the formational energy required for this calcium oxide to form? So, such compound specific, so this is the formation compound specific energy change, that is for the reaction at a particular standard temperature and pressure, and this is at another temperature pressure which is there at the prevailing conditions of your aquatic system. So, first thing we are going to do is we are going to derive a few equations, and I am going to move a little slow here so that you follow the how the equations are being derived. It is not at all complicated, just have to follow the equations, right? We just have to follow the equations. So, we will start with the basic first law. And what was the first law about? It says that the energy is neither created nor can it be destroyed, it can just be transformed from one form to another. And this was the equation that we have, that is the internal energy is equal to the heat, changing heat, plus the work done on the system. Now, this is plus therefore. So, heat and work is being done on this particular system, not by the system. If it would have been by the system, it would have had a negative sign. So, here are all the definitions I have provided for your easy reference at all times. So, that was the first equation that we write from the first law of thermodynamics. Then using the second law of thermodynamics, which talks about the entropy, we derive we have the second equation, that is dq is equal to T into ds. Now, moving ahead, now for reversible processes, dq is equal to T del S, and for irreversible processes the heat energy is less than the T del S. So, therefore, you have to do apply some more energy to make this into a forward reaction. That is why it is a irreversible process. Now let us talk about work done, because we are now going to the system has to have this component, right. So, dq we have, dw we are going to know. So, dw, what is work? Work is any kind of force into displacement. So, this is the equation. So, very general equation, okay, force into displacement and integration of the path, okay, because work is a path dependent function, okay. Now, there are two types of properties we have. One is an intensive property, another is an extensive property. What is an intensive property? An intensive property is a property or a characteristic that does not depend on the mass or the volume of that particular substance. For example, the pressure. If you are applying pressure, okay, then whether you are applying pressure, that pressure is an intensive property. That means it does not depend on the mass or the volume of the object on which you are applying that pressure, okay. But dV, that is change in volume, is definitely a volume related, mass related property. So, therefore, dV is a extensive property, while expansion, okay, that is minus V, that is growing, okay, that expansion is, the pressure is an intensive property. Similarly, in terms of chemical terms, okay, mu, which is the chemical potential, okay, mu represents chemical potential, and we will talk about mu in details in the next few slides. So, mu is an intensive property, that means mu of a substance, once we note it down, once we find it out, it does not depends on the amount of matter or amount of volume, okay. So, it is a volume independent and mass independent property, but the number of moles, okay, that is dN, the number of moles in that particular reaction, dN specifies the number of moles of that particular compound, or so that is a extensive property, that depends on the mass, right. The property mu I, okay, now we are going to talk about the property mu I is called the partial molar free energy or the chemical potential of a particular species, okay. It is the chemical potential, more commonly we call it the chemical potential of the species, and it can be written as delta G divided by delta Ni at a particular temperature, at a particular pressure, and in presence of other chemical constituents, that is Nj, okay. So, that is our Gi, the molar free energy of that particular species, okay. So, this is either represented by Ui or Gi, okay. So, we generally use this mu term. And how do we explain it? Okay, how do we explain it in physical terms? It is the change in free energy when adding an infinitesimally small amount of Ni while keeping all other properties and composition constant. So, suppose you are having a system, say suppose you are having a beaker, you are adding a few products and there is some reaction going on. So, some products are also being formed. So, reaction is forming some products, okay. Now, here you are adding a very small amount of one particular reactant, okay. So, let that reactant amount be Ni. Then due to that Ni addition, what is the change in the free energy of that particular system, given that everything else is kept constant? That is the understanding of mu I, okay. That is the chemical potential of that particular species, okay. Given these few definitions, let us derive the G term, okay. We are going to derive this del G term, because as I said, we need to find out this del G R, okay, and we need to understand our chemical equilibrium, okay. So, let us move on to this energy balance equation. Now, the energy balance equation can be written by combining the first and the second, both the laws of thermodynamics. That explains some kind of expansion and some chemical work. So, dE, that is the internal energy change, is equal to T del S minus P del V plus a summation of mu I into dNi, the change in the infinitesimally small amount of I species that you are bringing. So, this is your chemical work and this is your physical work. This is your chemical work and that is your physical work. Now, for a system with a fixed composition of the internal energy is a function of S and V, right. So, if the chemical composition is fixed, if this is fixed, then only your changes are happening in this and in this, right. Then what will happen? You are trying to measure delta S, which is change in entropy. Now, changing entropy is very difficult to measure. Temperature change, pressure change, volume change are easy to measure, but change in entropy is difficult to measure. Because of this, now we are going to rearrange our terms. Therefore, Gibbs introduced a Gibbs free energy, and he said G is equal to enthalpy minus Ts. Now, this H term, H can be replaced by H is equal to E plus PV. So, we are replacing H, that enthalpy term. So, we just replace H here and instead of H, we write E plus PV minus T del S. So, this is our. Now, at a constant temperature, what will happen? If the temperature is constant, now we are trying to differentiate. So, we are trying to differentiate. So, this equation, how it will change? At a constant temperature, if you are trying to differentiate, so dG, change delta, small change in G is equal to small change in enthalpy minus T del S. Now, how it will, this actually will break down to T del S and also dt into S, right. But since the temperature term is constant here, we do not have this term. At constant temperature, we are only left with these two terms. So, dG is equal to dH minus T del S. Now, what is dH? Again, dH is equal to E plus PV. So, we are going to H plus PV, this we have to again differentiate. So, now if we are going to write this equation, and we are going to differentiate into these terms, then this is our equation, dG is equal to dE plus P del V plus V dP minus T del S and minus S dt. So, this is our differential equation from this equation, right. Now, if we are going to rearrange, let us rearrange a few terms. So, here dE is there. dE, what do we know? dE is equal to T del S minus P del V plus summation of mu I into dNi. So, we are just going to replace this dE with this equation, and here we bring in T del S minus P dV plus mu I dNi. This minus P dV and this plus P dV, this minus P dV here and this plus P dV will cancel out. This TdS and this minus TdS will cancel out. So, we are left with dG is equal to V dP minus S dt plus mu I into dNi from this equation. So, this equation, this gets cancelled out, this gets cancelled out, this comes here, and from dE comes this term summation of mu I into dNi. Okay. Now, it is in terms of temperature, pressure, volume and chemical potential. Okay. Now, again as I said, if we are keeping our temperature as a constant function, then this also changes to 0. Okay. If we are keeping the temperature at a constant, then this term also becomes 0. Therefore, at a particular temperature, pressure, okay, whatever is changing, okay, we can easily measure it. Okay, we can easily measure that. Okay. So, at a constant temperature and pressure, free energy is only a function of the composition of the system, that is delta G is equal to summation of mu I into dNi. Right. So, at a constant temperature and pressure, both these terms becomes 0. Okay. And entropy is one of the difficult parameters. So, we are trying to find out a way such that we do not have to measure that parameter. So, that we measure the parameters which are easily measurable in the lab, such as temperature, pressure, volume, changing in chemical compositions, those things. So, now we have reached this particular equation. So, what is the free energy of a system? Okay. The free energy of a system is the amount of work necessary to reproduce the system from an arbitrary reference state. Okay. So, you are given an arbitrary reference state. An arbitrary reference state means the state at which say suppose at a particular 1 atmospheric pressure, at a particular 25 degree Celsius that temperature. So, that is your reference state. So, that is a reference state, and then you have to bring your system to the given prevailing conditions that your aquatic system is. Okay. So, that work that is done on that system. Okay. And in terms of the total free energy is the sum of the free energies of the constituent parts, that is the chemical constituent parts. So, G is equal to summation of mu I into dNi, that is the chemical potential, into change in the small molar composition of that particular species I. I is a chemical species. Okay. So, I is a particular chemical species. Okay. A system is at equilibrium when it is in its lowest possible energy state. So, always we are moving to our lowest possible energy state. Okay. So, the chemical reaction has to happen such that delta G is reduced. Okay. So, the G value should get reduced. Okay. Now, consider, let us now take an example of a reaction. How do we write it? Okay. So, consider a reaction, that is A plus B is equal to C. Okay. A and B is reacting to produce another compound called C. Okay. And there is a molar coefficient attached. So, 2A, 2 parts of A and 3 parts of B is required to form 1 part of C. Okay. Then how will the total energy be written? It will be written in terms of G is equal to number of moles of A into the chemical potential of A plus the number of moles of B into chemical potential of B plus the number of moles of C into the chemical potential of C, because it is a summation of mu I into dNi, right. So, you have to give all the A, B, C, you just go on summing that. So, that is how it is written. Okay. Now, if you are going to differentiate it, change, okay. So, small change, how much is this change in the free energy of the system due to an additional D and C moles of C. Okay. So, this is a small molar change that we are going to do, and we are going to see how much is the free energy changing. Okay. So, to do this we are going to differentiate it. So, dg is equal to, so how do you differentiate? When you are trying to differentiate, we are going to first differentiate one particular n term, keeping the other constant, okay, and then again going to differentiate the other term mu a, mu b, mu c, keeping the n term constant. Okay. So, dna divided by dnc into mu a is constant, plus dnb divided by dnc into mu b is equal to again constant, plus dnc divided by dnc is equal to mu c, and this again totally you are multiplying with this small change dnc, okay, plus na. Now, this term is constant and you are only differentiating with terms of mu. So, delta mu a divided by dnc plus nb into delta mu b by dnc plus nc into dux, oh sorry, this should be c, okay, divided by dnc, and the whole term again multiplied by dnc. Now, this second term ndi, if you can see that this particular term, okay, this particular term should be equal to 0, and this is called the Gibbs-Duhem equation. Okay. This particular term should be equal to 0, okay, implying that any closed system, one chemical potential is not independent. Okay. So, this you cannot do, okay, you cannot divide a mu a term with the nc term. Okay. So, this particular term will become 0, and this only this equation, only this part of the equation is called the Gibbs-Duhem equation. And again in physical terms, what does it imply? That in any closed system, one chemical potential is not independent and is given by the sum of the other species. Okay. So, one particular chemical composition if you are changing, that means that the chemical potential of the other species in that system will also change. Okay. So, therefore, this particular term becomes 0, okay, and that particular equation we call it the Gibbs-Duhem equation. Okay. Now, again, thus the incremental increase in total energy is given only by the first term, that is summation of mu I into dni. Okay. So, that is the change in energy. Okay. The other term becomes 0. For the generic reaction that is given above, so this is the generic reaction 2A plus 3B equal to C. For this particular reaction, how do we write? dG divided by dNc, that is a change in the chemical composition of C, is equal to minus 2 mu A minus 3 mu B plus mu C. Okay. As you can see, because it is a summation, so all the reactant terms will be in negative and the product term will be in positive, and whatever is there as the coefficient, molar coefficient, whatever is there, you are going to multiply that. Okay. So, 2A if it is there in that reaction, it will be 2 mu A here. If it is that in that reaction there was 3 moles of B required, so here it will be 3 times into mu B. Okay. The values of chemical potential, now let us move on to what is mu. Okay. How do we write chemical potential? What is the equation of mu? Mu is written in terms of a constant value. First of all, every time we are going to find out what is its value at a particular standard temperature and pressure. So, that is called the mu I 0, okay, that is a mu I 0, okay. And there is another term that is dependent on the concentration, because mu is the chemical potential of a particular species. So, that has to depend on the concentration term. So, for an ideal solution, mu I is written as mu I 0 plus RT ln Xi. What is Xi? Xi is the concentration in terms of moles, okay, mole fraction, okay, rather than moles it is mole fraction scale, okay. So, how much is the mole fraction you have to find out from that reaction, and that you have to write. So, Xi is the concentration in terms of mole fraction, okay. You do not write, okay, 5 grams of A or 2 grams of B, no. In terms of mole fraction, what is the concentration that is used. Now, when we are writing in terms of del G, the molar free energy change of a system depends upon the progress of the reaction, okay. It can be expressed as the standard free energy change given by the stoichiometry and the standard free energies, that the del G 0. So, this is the standard free energy del G 0, and the reaction quotient. What is reaction quotient? What is Q? Q is, so suppose if you are having this equation where you have 2A plus 3B is equal to C, then reaction quotient is C divided, so that is a product divided by the A and B, and this is to the power 2 and this is to the power 3, okay. So, this is the reaction quotient, okay, which is very similar to actually K in terms of equilibrium. If it is at chemical equilibrium, we write it as C divided by A into B, okay. So, whatever is the coefficient here, it will be to the power here, okay, it will be to the power. What is the difference between Q and K? Q is only at equilibrium, so we call this reaction quotient Q only if that is at a chemical equilibrium, otherwise we will say it is the reaction quotient Q, okay. So, Q and K are basically the same thing, only that one condition is not at equilibrium and the other one is at equilibrium, okay. So, delta G is equal to delta G 0 plus RT ln Q, okay, and delta G 0 is equal to minus RT ln K. So, since it is at equilibrium, so this G is represented by ln K and plus RT ln Q, this is at another temperature and pressure condition. So, here we are writing Q. Now, if we rearrange, okay, in terms of ln, so delta G is equal to RT ln Q by K, okay, ln Q by K, because here there is a minus sign. So, K comes into the denominator. Now, if we are moving from ln to log, then you write which is equal to 2.3. So, just change it to log terms. So, 2.3 RT log Q by K, okay. So, this is a very important equation and we are going to use this very often in thermodynamics, okay. So, you have to at least remember this equation, at least remember this equation. So, one equation, okay, this equation very important, this equation very important, this equation very important. Often you are going to be asked to calculate these, values, okay. So, try to remember these equations. I think you can find out, note the similarity in terms of equations. Okay. Now, let us talk about a little bit more into details about this chemical potential term. Okay. Since we are doing aquatic geochemistry, we are going to do a little bit, delve a little bit more into this mu term. Okay. Now, mu, what is mu? As I have already said, okay, in this previous slide we said mu I is equal to mu I 0 plus RT ln xi, right. So, this is a particular concentration, molar concentration. But when we are talking about solutions, we are talking about dissolution equations and all that, we are going to use this term, another term called A, and which is called the activity of a particular phase. Okay. It is not only concentration, but now we are going to talk in terms of activity, because we are talking in terms of solutions, dissolution equations and all that. Okay. For solutions, we are going to therefore define a more convenient scale. So, what is more convenient, what is more real, we are going to use that, and there we are going to use this term called activity. How is activity and concentration related? Activity of a particular species is equal to concentration of that particular species into its activity quotient. Okay. This is called the activity coefficient. Okay. So, A I is equal to C I into gamma I. Now, if we just replace A I in this equation, it becomes mu I into mu I 0 plus R T into ln, this is the A term that we have here. Okay. A I. So, A I we are replacing that with C I into gamma I. Okay. Now, if we just break this down, okay, into different terms, what is it called? This is the chemical potential, this is the standard potential at a particular temperature pressure, that is mostly 25 degrees Celsius and 1 atmospheric pressure. RT ln C I, this is the free energy of mixing, and this is called the potential energy of species interactions, because this gamma I, what is gamma? Okay. Gamma I is due to interaction. Okay. Let me tell you a little bit about the physical form. Okay. What is the difference between activity and concentration? Say suppose you have mixed a particular salt in water. Okay. A particular salt you have mixed, say suppose 1 gram in 1 liter of water. Okay. Say suppose X is the composition. Now, when you are dissolving this 1 gram in 1 liter of water, okay. Now, water, as you know, is a polar solvent. Okay. All X, that is 1 gram, will face some of that polar electrostatic effect when it is getting dissolved. So, when actually any reaction is forming, okay, when any reaction is happening, then not necessarily 1 gram is actually reacting. It may be 0.99 gram that is reacting. Okay, it can be, it is 0.99 or it can be anything, it can be 0.97 gram that is reacting. That 0.03 gram that is not reacting is maybe due to the solvent properties, okay, solvent properties of water, that is the polar nature, okay, and all the electrostatic effects that is happening, that is getting captured, that is capturing this much amount. Okay. So, always activity is lower than the concentration. The activity in a solution is always lower than its actual concentration, and this gamma I is actually calculated for every every salt, every acid that we know, it is calculated, and we have find out all these coefficient values. Okay. So, this is calculated from these these values. Okay. So, the chemical potential is always well defined with respect to some reference level, that is this one, okay, which is the elements in their standard states. Okay. So, how is mu I 0 how is it that calculated? That is calculated from the elements in their standard states. Both mu I 0 and gamma I require precise definition, and it can have different values depending on the scales on which they are defined. Okay. So, if you are changing 1 liter of water, if you are changing the temperature, if you are changing the pressure, this value will be different. Same thing, this again, this reference level, if you are changing, this will change. Okay. So, it is very important to mind the scales in which they are determined, and that for you to exercise when you are doing this particular calculations. So, the standard state for aqueous solutions, okay, that state is a very hypothetical situations. Okay. For that standard state, in that situation hypothetically C I is equal to 1, okay, and gamma I is also equal to 1. Okay. In the standard state for aqueous solutions, a hypothetical state is considered where C I, if it becomes 1 and gamma I becomes 1, what will happen then? If C I and gamma I both becomes 1, then A I becomes 1, right. So, from this equation mu I equal to mu I 0, we have RT ln AI, and this RT ln AI of 1, that ln terms become 0. So, mu I is equal to mu I 0. So, that is your standard state. Okay, that is your standard state. So, in your standard state, to find out this term, you have to make a situation where your concentration is equal to 1 and your gamma is also equal to 1, and this is almost not physically practically obtainable in a situation. Okay. So, now other than the standard state, we also have a reference state. Okay. In that reference state, we talk about a situation where the concentration can become very much similar to the activity. So, here only gamma I equal to 1, and in what kind of situation that can be? It can be in very dilute solutions. Okay. So, in very dilute solutions, gamma I is equal to 1, and therefore, the concentration you can consider it equal to AI. Okay. Also, for pure phases, okay, we are going to use molar fraction, the mole fraction as compared to the concentration. So, concentration is in terms of grams, okay, or milligrams, micrograms, that is my concentration. So, moles you are going to divide it by the molar concentration, and we are going to report the mole fraction only. Okay. As gamma I tends towards 1, Xi also tends towards 1. Okay. The mole fraction, as we are going towards more pure phases, my mole fraction also tends towards 1. Okay. Thus, when we are using pure phases such as pure water or a solid grain of pure calcium carbonate, the activity of water is equal to 1, the activity of calcium carbonate is equal to 1. Okay. Because here this is also equal to 1, okay, because gamma is tending towards 1, and here we have replaced Ci with Xi. So, my Ai, which is equal to Ci into gamma I, I am replacing it with Xi into gamma I, and both are equal to 1, okay. As this tends to 1, this also tends to 1. So, 1 into 1 is equal to 1. Okay. So, in pure phases our activity is equal to 1. Okay. Therefore, in this standard state, okay, in the standard state or reference state, my mu I is equal to mu I 0, okay, because of this particular consideration. That is, my x I tends to 1 when my gamma I tends to 1. With this, I will stop this lecture and we are going to continue this discussing more in the next lecture.